I'm going to put on recording. And we are going to start with new topic today. Hold on, let me get this, bring this back. Okay, then I'm going to share screen, okay. Yeah, so we are going to start with a new learning model. So this is called decision tree, okay, decision tree. So if you, let me turn this off. So decision tree, it's for classification. And there is another name. When you see that, that also means decision tree. So it's ID3, okay? So the name is iterative dichotomasa 3. Okay, and here it also says this algorithm invented by Ross Quillen, okay, and generated to generate a decision tree from a data set. So based on the name, you can kind of guessing is it's a tree structure, okay, and for this name, okay, dichotomasa, is it? So this is means divide, is it split? So based on this name, we kind of can guessing, is it? But you may ask, oh, divide by what? Is it split on what? Is it? So this ID3 decision tree is as typically used in machine learning and natural language processing domains, okay? And later on, there is an update, okay, extension for ID3 is called C4.5, okay, algorithm. So this is general idea about decision tree. The two other name you may see ID3 and extended version C4.5. Okay, so decision tree. What is a decision tree? Is it what it looks like? So here it shows a diagram. Is it? So like in this diagram, as it says, okay, so you're going to, so suppose for certain day, is it you decide what are you going to do, is it? So work to do, like, is it? So this we call it a node, is it a node? A node. And then you say, okay, work to do, yes, is it? And then it says stay in. If it says no, is it? So if you don't have work to do, then you're going to decide to go outside. Is it? But go outside, then you need to check the weather. Is it? So here is you are going to check weather. And in the decision trees over here, this shows, we call it an internal node. Okay, internal node. And then it says, okay, if it's sunny, is it? Then you say, okay, I'm going to go to beach. Okay, so you already decide what you're going to do. And for this node, it doesn't have any more extension. Is it? No more extension here. So this we call it a leaf node. So we have internal node, is it here, and we have leaf node here, is it? And it's overcasting, okay, then you go running, is it? And if it's raining, then you're going to see, check with friends, is it? So over here, says this is called a branch, is it? Because you haven't to make a final decision, is it? So if friends also busy, then you're going to stay in. Otherwise, you're going to go to movies with friends, is it? So this kind of structure, is it? It looks like a tree, and you make a decision, is it? Based on, later on we will see for like, because regarding machine learning, we have features, is it? We have features. So basically, you're going to make a decision based on the features values. And from this decision tree, if you recall the previous machine learning models, is it? And especially later on, we will learn like neural network. Is that for decision tree, it has advantage. Here I highlighted it. It's very good on interpretability. So you can get quite a clear picture, is it, why you reach that decision, is it? And then it says break down data by make a decision. Is it based on a series of questions? This is a series of questions. So here's a series of questions. It's based on basically it's features. Okay. So this is just a general idea about the tree as it look like. And like over here, it highlights, is it? So for the decision tree, it's a white box here, like here it says. Oh, I didn't get to the annotation. So this is a white box machine learning, is it? Because we can see internal decision making logic. You remember we have the internal node, is it? Internal nodes, is it? So it's not just the final decision, is it? And this kind of thing says it's not available in other algorithm. Is it like a neural network? That's a black box, okay? And also it says here, advantages the training time. It's also fast. The training time is faster, etc. And decision tree is also distribution free, okay, and non-parametric type method. So it does not depend on, previously you remember we also learned, is it like logistic regression, as it's a probability, but over here there is no probability distribution assumption, okay? And because of the, like what we just see, is it the decision, the internal node is based on the features. So decision tree, it has an advantage, like over here says, why I cannot do draw. Okay. I don't know why I cannot draw. Okay, so it has the advantage it can handle high dimensional data with quite a good accuracy. Okay, so that's the general idea about decision tree. And then later on, we will also see. So decision tree, it's a transparency, is it? Because we can see internal decision, that, and also relative low computational cost, is it? And the decision tree, because of the internal decision, it's transparent, is it? So decision tree can also be quite useful for explore data before we apply other algorithms. So a lot of time for machine learning, you're not just use a single model, okay? You may apply multiple models and to do something, etc. And so here is another quite useful feature for decision tree is it can check the quality of engineered feature. So it can also be quite useful for what? For feature selection. Okay, so this is, let me see, why cannot, okay, now it's a pen, okay. So for this regarding, so this part, what it means is it can also help do feature selection. Okay, because a lot of time for some data set, is a data set, you may have many features. There's many features. So what's the important feature? How do we pick out important features, etc.? So one way we can do is we can use decision tree, okay, decision tree. And the downsides of decision tree, like over here it says, it's tended to do overfit, okay, because later we will see an example that if you have a very deep tree, that so it's not easy to grasp the relationship between features, okay, because of the overfitting, etc., and the use of the greedy learning algorithms. It's not like, you remember when we learned the global minimum model. I don't know if you still remember the name for the global minimum. Is we learned the gradient descent. Is it? So over here in decision tree, we don't have this like a global minima. Is it? Global minima. Is it? We don't have that cost function to find the global minima. Is it? So it's approach the learning from a different way. Is it? So this is decision tree classifier, okay. And then the next question is, okay, so decision tree, you remember the name is ID3, is it? So that D dichotomizer, is it? Dichotomizer means split. It means split. So you split on what? Is it like over here? You're going to split that on feature, okay, on feature. And the feature, how do you split? Based on what criteria is it? So we are going to use, we call it largest information gain, okay? So for decision tree, it's information gain. So this is what it's used for. Instead of like a gradient descent, as a gradient descent, we use cost function. Is it cost function? As here we don't. We call it information gain. Okay, information gain, and it is an iterative process. Is it because you have a tree needed to build? Is it? So for sure, it's an iterative process. So you're going to split the splitting. Is it? At each child node until the leaves appear. Okay, so what does this mean? The leaves appear. So the ultimate goal here is the leaves appear means the set of data, not the whole set. Okay, so part of your data. So set of data belongs to a single class. Later on, we were seeing our examples, okay, because then we said, okay, this node, you cannot divide anymore because of the set of the data, this set of data belongs to a single class. Then we say, okay, it's a leaf node and it's pure, okay, it's pure. And how do we prevent? Because we just said one of the drawback for decision tree is overfitting. Is it to prevent overfitting? One way we can do is by set the limit of the maximum depth of the tree. Okay. So this is okay. Then next, let's see. So we previously discussed, is it? So the split is based on information gain, the information gain. Okay, so over here it says the objective functions is that information gain. So it's maximize the information gain at each split, is it? So here we have this mass expression, okay, the mass expression. So this information gain here, we also have P. So P, so this P represents parent, okay, represents parent, and the F means for feature. Is it because you remember we have this node, is it? Then you have branch, is it? So this is parent, is it? And this is a child node, is it? And it's all based on feature, is it? Based on feature, you're going to do split, is it? Split. So over here, this is the information gain, as if for the parent. And then over here, so this n is a number of a certain class, okay, of the number of the children. So over here we have, over here, is it? And this nj. So this nj is a number of samples in the j's child node. Okay, j's child node. And the np is a number of samples at the parent node. Is it? So you have the parent node, the total number of samples in this parent node, and then it's going to be splitted. Is it going to be splitted based on the feature? Is it? And then over here, like nj is a number of samples in the j's child node. So in this one, is it? And so you're going to sum all of them for all of the childs, is it? So information gain is simply the difference between the impurity of the parent node, is it? And the sum of the child nodes in impurities, is it? And of course, if this item is smaller, is it? Then this information gain, is it, is going to be larger, is it? So the whole point is to get this value, is it, larger, is it? Okay, so this is objective function, so it's our information gain, how to calculate it, the general formula, okay? And then generally speaking, and in sklearn, okay, we generally use binary decision tree, okay, not a multi-way decision tree. So we are only going to consider left child and right child, okay. So it's impurity of parent is a minus impurity of left child and the right child, okay. So that's for the binary decision tree. And generally to calculate the I, is it? So I. So I is the impurity, is it? So I is impurity. Here it says there are 3 impurity measures, okay. One is called Gini impurity, so Ig. And one is entropy, so IH. And the third is classification error, IE, okay. So we will see all these 3. How do we calculate them? So first is the entropy calculation, okay. So the entropy calculation, so here T is for specific, for a particular node, T, okay. So it's a tree, is it? So generally it's a tree. Here you have the tree, you have the node, you have the node. Looks like this, is it? So the T over here, so T represents some node, okay, some particular node, okay. And then what over here, the C is for what? So is for certain class, because over here we are going to do classification, okay, classification. So over here it's based on the probability calculation. So at a certain node, is it a certain node, number of sample or probability of the samples belong to certain class, okay. So that's regarding this probability. So that's the formula for entropy calculation, okay, entropy calculation. And over here it says the entropy is going to be 0 if all sample at a node belong to the same class. Okay, so be careful here. If this node is pure, basically, is it, then its entropy is going to be 0 because it's all belong to the same class. And the way it's going to be maximized, so if you have a uniform class distribution, okay, so if it is distributed evenly among all of the classes, then your entropy will be maximized, okay. So here it says the entropy criteria attempts to maximize mutual information in the tree, okay. So this is for the entropy calculation. And the second one is what? Is Gini, okay, Gini impurity. Gini impurity, over here, it also gave us the formula to do the calculation. Is it? It's similar. Okay, so T is for the node. T is for node. Okay, I is for the class. So which class is it? So this P represents the probability. Is it at node T? At node T, is it? And belong to some class C, is it? So that's what this probability. Okay, so Gini impurity, then it's based on this probability calculation. Okay. So it's a kind of, right now, it may not be too clear. Later on, we will see our example. Okay. And the third one is the classification. Okay, for the classification, it's not going to consider all of the classes here it shows. Is it? So it's just going to pick whichever is the largest, the probability. Then it's going to use 1 minus that. Okay, so this is for classification. You use classification arrow for the impurity. Okay, impurity. And then how do we build the decision tree? So it says the deeper the decision tree, then the more complex the decision boundary going to become. Is it easy tend to go over fitting? As they go over fitting, and also with decision tree, feature scaling is not required. Okay, so this is also a huge difference of, between decision tree and the previous models that we learned. Is it for gradient descent, we need to do feature scaling first. Is it, otherwise your model cannot perform well. And in sklearn, okay, also allows to export the decision tree. So we can also visually see our tree, okay. And over here, we will see our example. We use a GraphViz program. Okay, so this is regarding decision tree, and we're going to come back later, okay, about random forest. So next, let's take a look at the example first. Let's first take a quick look. Okay, so over here, so this, you remember previously we discussed the example about that so about that iris flower, is it classification? So we have 3 types of flower. Is it setosa? Is it versicolor? Is it? And over here, virginical is 3 types. Is it? And the feature, we have 2 features. We have 2 features. 2 features. Is it? It's what? It's about petal width. Is it? And what? And petal length. Is it pedaling? So basically over here, this is our example. Okay, the example, we run it and we generated this decision tree. If you take a look, at the very top. Is it? So this is a parent node. Parent node. Is it? What is the feature? What's the features is that, okay, if the paddle width is less or equal than 0.75, is it? How are you going to do with the, so this is a total number of samples. Is it? We have 103, is it? Samples, is it? And we have the values, is it? That's what we provided. Okay, 35, 35 for all three classes, is it? And for, in this case, the class, is it? You want to see if it's settled class, is it? Settled class. Okay, so that's a total samples, is it? And here the result also gave us the entropy, is it? The entropy. So that's the information gain. So calculation, is it? Calculation, and in this case is use entropy. Okay, it's using so the impurity calculation is, so impurity calculation based on the entropy, is it? So for the information gain. So we also, so the example, so the model also gave us the entropy value in this case. Okay, for this case, they said, okay, if it is true, is it? Then it lead to this node, is it? For this node, you can see the entropy value is 0, is it? How many samples we have? We have 35 samples, is it? And for the value, you can see the 35 all go to some single class, is it? Settled, is it? So this is a leaf node. Leaf node, is it? And it's, and we can see the total sample is 35, and all the 35 samples go to some single class, is it? So all samples go to that class. That class, is it? So this is leaf node. So we said this is a pure leaf node. Pure leaf node. So we have no way to do split anymore, is it? So no more split. Is there no more split? Okay, so that if the feature paddle width is less than or equal than 0.75, if it is not, then it says, okay, if it's false, then it go to this branch, is it? So this we call it a branch, is it? Then for this branch, the feature selection changes. As a feature selection, okay, it's regarding paddle length, not paddle width anymore, is it? Okay, if paddle length is less than or equal than 4.75, is it? And it's regarding the 70 samples, because over here, this branch get 35 sample, and all of the remaining samples go to this branch, is it? And for the result of this internal, so this is the internal node, is it? And for the result, you can see, is this total sample, it's just classified as for the second class and the third class, is it? So it's not pure, is it? So this is not pure. Is it? Not like the leaf node, it all go to that single class, as they go to single class. So it's not pure, okay? So the classification at this internal node you want to do is you want to classify if it's Vassar color, is it? And then it goes further, is it? And over here we said we do binary decision tree. Is it? Binary decision tree, is it? Okay, then the next one, you can see entropy changes to 0, is it? And this total sample is 30, it all go to that single class, is it? So this is also pure, is it? Pure leaf node, is it? So you can stop here. Is it? Stop here. And the same thing for the remaining samples, is it? You are going to further check, okay, if the petal length is a feature, you move the feature to its boundary value, is it, to a different boundary value, is it? Then in this case, you can see it's not pure, is it? So you then still need to do split, is it? So this shows, so for the decision tree, is it? And based on the feature, is it? Then you can do split, you can do split. And if, and we can also see if the entropy value, is it, over here, if it's 0, then you can get a pure classification, the leaf node, okay. Okay, so this is regarding that result. And next, let's see, how do we do in our coding, okay. In our coding, okay. Okay, still for that iris data, previously we already learned, is it? So how do you retrieve the data, is it? And so for the decision tree, whenever we want to use, we can import decision tree classifier, okay, from sklearn, okay, from sk. Then we set up the model as a decision tree model. And here you can specify, you remember we have 3 different ways to calculate information gain, is it information gain? You can, so here it says Gini, is it Gini, and we also have entropy, is it? And we have classification arrow, is it? That generally speaking is about the 3. Okay, so over here that's okay. I'm going to use Gini, is it, for the information gain calculation and maximum depth. So here it's the depth of the tree. Depth of the tree. Okay, you don't want it to be too deep in this case. Random state, we already see. If you set it as 1, is it? So then your model can be repeated. The pattern going to be the same, is it? And over here, then you just fit, is it? Fit the train. So this is a feature for the features and for the targets. Is it target feature value and target value? Is it? Then we can fit, and then you can collect the accuracy score. Is it with the testing data? Is it testing data? And over here it also draws the model after the training. Is it? So we can take a look, but so here it shows the boundary, okay? But what over here we are going to see is, previously, I'm not sure if you still remember, we said the decision tree can also be used. So decision tree, it's also quite useful for what? For feature selection. Sometimes we also call feature engineering. And in this case, it's not too obvious because we only have 2 features, okay? So generally speaking is, if you have too many features, is it? And maybe some features, so some may be noise, is it? So how do you filter out noise feature, is it? So that's, we can borrow this. And to get to pick out like the features importance. So from the model, so this is our decision tree model. Tree model that we trained, is it? we trained. And there is a parameter you can collect. It's called feature importance. Okay, feature importance. So it will list the percentage of the features placed in the model. Okay, in the model. So over here, because in our case we only have two features, that the pedal length and the pedal width. Is it? So those are the two features in this case. Is it? So the length of the importance is this importance collect all of the features. Is it the percentage? Is it among the model? Okay. So the total length is just 2. That's we only have 2 features, but we will get the corresponding percentage. Is it? So over here we do the bar drawing. Okay, we do the bar drawing to show. Then you can see the graph. Is it to see how important each of the feature. So over here, that's what we can see, is it, with the bar, is it? And clearly, is it clearly, even from the output, you can also see, is it? So this is the second feature, is it? So the second feature, so this is pedal width. Pedal width, is it? So it from the bar draw, is it? You can see the percentage of the importance takes more, as it takes more. So this is regarding feature importance. Okay, you can also retrieve the importance of the feature after you train the model. And next, let's see, you can also specify the criteria. Is it? Because we have 3 different ways, is it, to calculate the information gain, is it? So you can also try with second entropy, is it? And you can see the result is pretty similar, is it, for accuracy, is it? And then same thing, we can do the feature importance, is it, collection. So here it gave us, so with the entropy, you can see more, so the difference a little bit of more, is it? So the second feature, pedal width, it's placed more than 30% row, is it? For pedal length, it takes about 37%, is it? So with the bar, we can also clearly see, is it? So over here, this example just shows how do we do decision tree. So it's not too comprehensive here. You can see with the sklearn model. And then what next? Let's see. We haven't see how are we going to do the calculation. We just kind of briefly discuss the concept. So next, let's see. So next is to take a look, a very simple example about the calculation of information gain, is it? And previously we said, how do we do the split? Is it because decision tree is based on split? Is it? So how do you split? You try to maximize the information gain, is it, at each split. So that's our objective, is it? So you remember for gradient descent, is it? And it's to minimize the cost function. Cost function, is it? And here is what? Here is maximize what? The information gain, okay? So each model, they have different goals, okay? So this is the information gain, is it? So this is for parent, is it? Parent, and this is regarding feature, is it? So it's parent's impurity, is it? So this is parent parents' impurity minus what? Minus the summation of all of the what? The child's. This is child's. So children's. Is it children's impurity? Impurity. Okay, impurity. Okay, and we said we use the binary decision tree. So you're going to just minus left and minus the right. Okay, and the formula for binary list like this. Is it? So let's see. Okay, what does that mean? Okay, so here we have an example. Okay, so total sample we have 80. Then we have 80, and here it's based on certain feature. Is it? And then you're going to do split. Is it? You're going to start a split. Is it split based on feature? Okay, suppose you remember for that example, okay, is a length less than equal than 70.5. Is it something like this? Is it? Then it can clearly split 40 and 40. Is it? So suppose this is yes. Is it? So 40 will go less than. Is it? And the other 40 will not meet. So this is no, is greater than. Is it? And then over here, you're going to do split again. You can. Is it? So maybe this is some other feature. Is it? Then length. Maybe. Is it greater or less than something? Is it? Then it's going to be splitted as 30 versus 10. Is it? Then in this case, it's going to be 10 versus 30. Okay. So this is this case. This case. And so this is case B. Case B, is it? So you still have like 80 samples, is it? But this time maybe the feature is not the width. Maybe you start with length. Is it? You start with length. Okay, you said length greater than 3.0 something. Is it? Assuming. Then your decision tree is going to look like this. Okay, look like this. So for the decision tree, so it's how you split. Is that you select the feature and their value, and then you do split. Then the tree, you can also see the generated tree also going to be different. Is it? So our goal is to find what? To find which one has a maximized information gain. Then you're going to pick that tree. Okay, so that's the overall goal. And then let's see, how do we do the calculation? Is it? And here, what we are going to do is we are going to use what? Use the impurity. That's the error one. Classification error. Is it? Then in that case, it's 1 minus the maximum value of the probability. Is it? Belongs to certain class. Is it? And this is at which node? Is it? Okay, then over here, you see, this is for the parent impurity calculation. Is it? Because the probability, you do the split half-half. So it's 1 minus 0.5. Is it? The maximized probability. Is it? So it's 0.5. So you get 0.5. Is it? Okay, then for case A, is it? Case way over here, you see, we have 30 over 10. Is it? 30 over 10. So the maximum probability, is it? So it's, you have 3 over 4, is it? And you also have 1 over 4, is it? Because it's a 40, is it? So the probability calculation over here, you use 30 over 40 and 10 over 40, is it? So that's why we cross out, we have this 3 over 4, is it? So that's the, we are going, so you have this 2 probability, is it? After you do the split, is it belong to certain class, is it? So because we here going to pick the maximum one, so that's why over here, we pick 3 over 4, is it? Then you get, okay, the impurity for the left. So this is impurity for left node. Is it? It's 1 minus 3/4. Is this so 3/4? So that's why you get a quarter. As they get a quarter. So same thing for the right one. As if for the right one, we also get a quarter. Okay, for the impurity calculation. And then similar calculation for the case B. Okay, case B, be careful, it's 2, 4, is it? And the other is 2, 20, 0, is it? The ratio. So that's why for the left part, is it? It's, so for the left node, is it? So its impurity calculation, is it? It's because the ratio, is it? The ratio is 2/4, is it? So that's why the probability is 4/3, is it? That's a maximum one, okay? So that's how you come up with this impurity calculation. And for the other one, is it? Because it's just a single class, as it's pure. So that's why it's 0, as it impurity is 0, okay. And then for the information gain, then we apply that parent. So this is for the parent one, is it? And these two are from the children's, is it? So that's how we come up with 0.25. But if you compare both of this, these two are the same, is it? So then in this case, you can do either split. You won't have any advantage, okay, in this case. Then let's see. If we use Gini impurity to do the calculation, so here it's the Gini impurity calculation, is it, with the probability, then we will see for the parent, then it's, so in this case, then you need to include not the maximum probability, is that you need to include all cases, is that, so that's why it's 0.5 square, okay, in all cases. So same thing for case A, is it? For the left, you need to consider both, is it both? And then for case A, is it? Its information gain, then we can come up, this is its information gain, it's 0.125, is it? So that's for case A. Okay, it's Gini impurity information gain. And then for case B, if you do similar calculation, is it? And then we can find that its information gain is 0.16, is it? Then if you compare, is it? If we compare, so over here, for case A, is it? So case A is 0.125, and for case B is 0.16, is it? So definitely this is greater than the 125, is it? And this is information gain, is it? And our goal is to try to do the split with the maximized information gain, is it? So then if you compare, then you will say, okay, this is larger, so this is better one, is it? Better one. So you can pick, then you can pick case B, decision tree, is it? For your classification, okay? So this shows for the second way you do the information gain calculation, okay? And then same thing for the entropy, is it? That's the third way. So we can apply 3 different ways to do the information gain calculation. So for the entropy, is it? For the entropy, it's similar, is it? Similar. And here just to say, if all sample belong to the single class, then its impurity calculation is 0. If uniform distribution, then it can be the maximum. Okay, so that's regarding impurity calculation. Okay, then here similar thing, we do the parent one calculation, is it? And its impurity is 1. And then you do case 1, so you just plug in the corresponding value, is it? And the information gain, we can find it's 0.19, is it? And for case B, then its information gain is what? Is 0.31, is it? Then similar concept as previously, is it? So for decision tree, is it? Decision tree, how do you build the tree? You do the split. Is it? Split on what? Split on your samples. Is it? On samples. Is it? And how do you split? You use the information gain to split. Is it? And the goal is to what? To maximize the information gain. Is it? Then clearly we can see this information gain is greater than the 1.9. Is it? So case B is a better case. Is it a better decision tree? Okay, in this case. So this tree is better. Is it? Okay, so here we kind of get the idea about how do we do decision tree, general idea. And I think that's a major material for